Okay, good afternoon, everybody. So we're on the types PowerPoint. Yep.
On this assignment and the last, it doesn't say what's named a zip file.
It doesn't matter what the zip file is named. Yep, as long as it's a zip file. Types. Okay, so we're on the types PowerPoint set of slides. All right, so you should all, by this point, know what a type is, right? So a type defines a set of values that an object can have and the operations that you can do with the object, right? So int is a type in both Java and, well, Java, Python, and C, right? It represents an integer type, so those are the set of values, right? You know that in Java, there's a finite number of ints, right? In Python, there's a finite number, but the number depends on the amount of memory you have. In C, it's also a finite number of ints. Right? And there are certain things that you can do with an int, like arithmetic and comparisons and so on and so forth. So there's a link embedded in this page, which takes you to the documentation for the arithmetic type. So these are all the numeric types in C, right here. So notice that without reading it in any detail, if you quickly look at it, right, you see that the Boolean type, so logical types, right, true, false, in C is actually a numeric type. Right, which is different than in, well, it's different than Java, right? So in C, your Boolean type is actually an integer value. Right? We'll talk a little bit more about this shortly. Right? Notice that the character types, just like in Java, are also integer values, right? So remember car from Java looks like the characters of a string, but they're actually implemented as numbers, right? Integer types, unsigned integer types in Java. Right? And so that's true in C as well. But now notice that C's got this funny unsigned and signed version of its integer types. Right? So you can have a signed integer type and you can have an unsigned integer type. Right? So a signed integer type can take on negative values. Unsigned integer types cannot take on negative values. So if you quickly look at the integer types, you'll notice that there are many more types than there are in Java. Right? So you have something called short. Well, you have short in Java as well. But you also have an unsigned short. Right? You've got int and unsigned int. You've got long and you've got unsigned long. And you also have long, long and unsigned long, long. Right? So there are more types in C than there are in Java. Right? And also the name of the types, the same type can have many different names in C. Right? So in the middle column, that's the type that you probably should be using. In the right-hand column, that tells you the equivalent types. Right? So if you want a short int, so that's an int that's probably smaller than that's a type of integer that's probably smaller than a regular int. Right? You could also call that short int, signed short int. Right? So there's like 4 different names there for the same type. Right? Similarly for int, you can use int, signed with nothing else after it, or signed int. Right? So you should generally stick to the middle column. Now the funny thing in C is that if you look at this column over here, right, so the width or the size and the amount of memory that each one of these types take, there's no fixed value here. Right? So in C says that a short should be at least 16 bits, right? So 2 bytes or 16 binary digits, right? So it says it should be at least 16 bits, but it doesn't say exactly how many it should be. Right? Similarly for an int it says it should also be at least 16 bits, but again, it doesn't say exactly how big it should be. Right? And so this is the big difference between C and Java. In Java, the primitive types all have fixed, well-defined sizes. Right? So in Java, an int is 32 bits. Right? A long is 64 bits. Right? And in C, it just says, well, it's got to be at least this big. Which is, well, was one of the slightly annoying things with working in the C language. Right? You never really know, well, you might not ever know how big your types actually are. So notice there's 4 more columns. So these are the common operating systems and architectures, and this is how big the types actually are in these architectures. Right? So that column LP32, that's the old Windows operating system, which isn't used anymore. I don't even know if you can find a working, well, that's a very, very old version of Windows. that column there is the 32-bit version of Windows. That column there is the 64-bit version of Windows, I think. And that column over there is the 64-bit version of Linux. Is that right? LP64, yes, is Unix and is Linux. Right? So in these systems, the sizes really are well defined. Right? So they really do have well-defined sizes. However, you can't rely on that. Right? So if you write a C program, when you move it to a different architecture, right, that same C program may not behave the same if you've made assumptions about the size of your values. Right? So for example, if you take here's a good one. Right? If you take a program written in Linux on a 64-bit operating system in Linux, right, and you use the value long, right, then whoever's using that, when you code in Linux, you're probably expecting it to be 64 bits long. But when you take it to a 64-bit Windows system, it suddenly becomes 32 bits. And any assumptions that you may have made may cause your program to break. Right? So all of the overflow issues that you have in Java with the integer types, you also have them in C. It's slightly worse because you don't always know exactly how big your ints are. Right? OK, and then there's a few more. So then there are the floating point types. So there's float and double. That's the same as float and double in Java. Right? And then you also have long double, which depending on your operating system, may or may not be bigger than double. Right? So float is a 32-bit floating point number. Double is 64-bit floating point number. And long double is supposed to be 128 bits if it's supported. OK. All right. So as far as the integer and floating point types, how they work in C and Java, well, it turns out they work the same. Right? They have the same overflow issues. The integer types have the same overflow issues. They have the same finite number of bits issues that you run into. It's just that the exact sizes are different in C. The operators are all the same. They behave slightly different in very unusual cases. But I'm never going to ask you about those, and they shouldn't really occur. Those unusual cases should not normally occur in well-written code. The floating point types behave exactly the same in C, Java, and Python because they all rely on the IEEE 754 standard. OK, if you want to know how big a type is on your particular architecture, you can use the size of operator. So size of queries the size of an object or type. Now what you have to remember here is that size of always reports sizes not in bits, but in multiples of the size of car. Okay, so multiples of the size of. So when you use size of and you ask size of car, it's always 1. Right? That's what the standard says. So the standard says the size of car is always 1. What it actually means is that a size of car is, well, I'll just leave it at that. It's always 1 for size of car. Normally, a car is 8 bits. Right? OK, so there's a little program there where you can run and then find the size of each one of these values. OK, so I guess quick commentary here. I'm using printf to print out the values returned by size of. Size of, it turns out it returns a type. It returns a slightly unusual type. It returns the type size underscore t. So size of returns that as its return type. That's just an integer type. It turns out it's normally 64 bits on any operating system that you would be using. Right? So to print out a long, that turns out to be a long int in Linux anyway, in 64-bit Linux. So to print out a long int, you need LD as the conversion specifier. Right? So remember, D is just an int. LD is for long int. Right? And so to print out one of these things, you need to use that conversion there. Right? So if you just run the program, you can find the sizes in multiples of car for all of these types. Right? And I've got that little program right here. So we can just run that. So it's already compiled. Right? So when you run that, you see that the size of car is always 1. Right? The size of this funny thing underscore big B bool, which is the Boolean type in C, that's also 1. Right? On this computer, short is 2, an int is 4, a long is 8, a float is 4, a double is 8. Now, the pointers on my computer, right? So car star, double star, those are pointers to something, right? Pointer to car, pointer to double, right? It turns out the pointers, any pointer type on my computer happens to be, the size of happens to be 8, right? So if car is 8 bits, then my pointers are 64-bit pointers on this computer, right? It's probably the same on all of your computers, actually. So if you're running on a Mac, it's almost certainly the same. If you're running on a virtual machine or Windows, if you're using the 64-bit version of Linux under WSL, it's also going to be 8. Okay? But if you take this to a different computer and a different operating system, you may get different values. All right, so what's this Boolean type? So the Boolean type in C is an integer number. Right? And believe it or not, there was no Boolean type until C99. Right? So for 20 some odd years, C programmers got along just fine without a dedicated Boolean type. Instead, they would use the numbers 0 and 1. Right? So 0 is false in C. Right? Any non-zero value is true. Right? Now, for the bool type, the value corresponding to true is 1. Okay, so if you make a variable of type underscore big B bool, right, and assign it an integer value, that value always gets converted to 0 or 1. Right? Sorry, if you assign it a numeric value, that value always gets converted to 0 or 1. So I'll show you an example of that in a second. Underscore bool is awkward to write. So if you include standard bool, you can just use little case b bool, right? And you can use true and false. Right? If you don't include standard bool, then you can't use false and true. Right? You have to use numeric values. Right? The Boolean types otherwise behave the same as they do in Java. Right? So you can have not, and or, right? Just like you do in Java. Okay, so here's an example of using underscore big B bool. Right? So here I've got underscore big B bool flag equals 0. Now remember, 0 is false. Right? So this says if flag, so if flag is true, print true, otherwise print false. Right? So if you run that, and assuming I have the right version of the program compiled. Oh, so I changed it, so it's true. Okay, so I'm going to set that to make it the same as the slide. And then recompile it. So what is that? That's boo. Okay. GCC minus o boo boo dot c. Oops. Oh, right, I can't do that, sorry. C can't use false, have to use 0. Okay, recompile and run. So this is going to print out, not surprisingly, it prints out false. Right? Right, so if the flag is false, it prints out false, and 0 is false in C. Right? If you change it to true, so if I change that flag to true, obviously it's going to print out true. Right? I'm not going to bother doing that right now. Right? But it will print out true. Now, one of the awkward things with working with the Boolean type, or C's Boolean type, is that it's really just a number. And it turns out there is no conversion specifier for the Boolean type. Right? There's no conversion specifier because printf is a very old function. When printf was first defined, right, there was no Boolean type. Therefore, there is no conversion specifier for the Boolean type. Right? So when you want to print out a Boolean value, you end up printing it as a number, either 0 or 1, which can be confusing, right? Because all you see are zeros and ones instead of what you'd probably prefer, true and false. Right? So when I print out this thing here, I don't remember which one this is. It's probably boo. Oh, sorry, control. Let's find out which one it is. So that's, oh, I'll come back to that one in a second. And that's not a good one either. What did I do here? Okay. So this is boo3. So for a true value, it prints out 1. Now what you'd really like to print out is true, probably. Right? But there's no good way to do it in C. The closest that you can come is the following. Right? So when you print out the value of the Boolean variable, what you can do is you can instead substitute a string for the Boolean value, right? So I can use %s, right? And then I can use this funny operator, which I never told you about in Java in 124, but which you might have encountered. There's the $:colon operator. So this is what's called the trinary operator in C and Java. So the way you read this is, right, there's some condition here, right? So something that evaluates to true or false, right? If that thing there is true, you get the value that's here, right? So in this case, if flag is true, I get the string true, right? The colon is otherwise. So if flag is false, I get the string false, right? So in other words, if the flag is true, all of this gets replaced with true, right? And if the flag is false, all of this gets replaced with the string false, which I can then print as a string, right? And in that way, you can print, right? You can print true in this case, right? Which would be nice if there was a way to do this without having to go through all of the, without having to go through the trinary operator, but there isn't, unfortunately. Right? You'll also notice that so printing stuff in C is a lot harder than printing stuff in like Python or Java, right? The Python function print and the Java system.out.println methods, or the toString method in Java, they do a lot of work for you. Right? There's an enormous amount of work that happens to generate the string representation of a floating point number, for example. None of that happens for you in C. If you want to do something in C, you have to do it yourself, right? Or find a library that does it for you. Let me go back quickly. There was another thing. Oh, right. Let me show you this program here. Let me show you this program here. There you go. OK. So remember that these Boolean values, they are just zeros and ones, right? So the way that the standard is defined, it says that if you assign any non-zero value to a Boolean value, so in this case I'm using a double, right? That value automatically gets converted to 1, right? Any value that's 0 stays as 0, right? But any non-zero value automatically gets converted to 1, right? So if you were to actually print out the flag here using %d, you would get 1. And this, of course, prints true, right? Because 0.001 is not 0, so it's true. Right? So boo2 prints out true. Don't do this, by the way. Sorry. Right? So you should generally avoid doing stuff like this. Right? If you want a Boolean value, assign true or false. Right? Don't do something funny like assign a double value to it. OK. So that's the Boolean type in C. Now what about the char type? So char is similar to char in Java. Right? So it's the type that you normally use to represent character data. Right? The standard says that char is the smallest addressable unit of the machine, whatever that means. Right? That's an issue for your CISC220, right? Where you learn about, or I guess computer architecture. You might learn about it in architecture. Right? So on most modern computers, the smallest addressable unit, that means the smallest piece of memory that your computer can actually access is 8 bits. Right? So on most modern computers, you cannot access an individual bit somewhere in memory. Right? You can get 8 bits somewhere in memory, but you can't normally get 1. Right? So char is normally defined as 8 bits. It's not always the case, but on any computer that you would be using, certainly in this course, it's going to be 8 bits. Right? Just like in Java, a char literal, it's just a single character inside of single quotes. Right? There is no such thing as the empty char, right? So you can't write single quote, single quote. That doesn't work. Right? And you can also use the escape sequences like you might have seen in Java. Right? So if you have an unusual character, those are denoted by the backslash. Right? It's just like you, similar to how you would escape a character in Bash. Right? So if you want the char, that's the single quote, you have to escape the single quote. Right? Similarly, if you want a char that's a double quote, you have to escape that as well. You might wonder why you have to escape the question mark. It's because of these strange things called trigraphs that exist in the language. Right? Google trigraphs if you want to know what one is. You're never going to see it in this course. Right? You probably will never see it in practice either. If you want the backslash, it's backslash, backslash, and so on. The other interesting ones are backslash n, right? That's new line, and backslash t, which is the tab, right? Otherwise, most of the other ones on the page are uncommon. So what about the enumerated types? So if you're taking 124 now, you have not come across enumerations yet, right? So this will be new to you. If you took it last term, or sorry, if you've taken it previously, you should have seen it. If you took it in the summer, you probably didn't see it, right? So there are these things called enumerated types. Basically what they are is you can assign a name to some integer value for a set of constant values, right? So here's an example, right? So I can make this thing called enum day, right? Where the value of day can take on the values sun, mon, tue, wd, and so on and so forth. That's actually 0, 1, 2, 3, 4, 5, and 6. Right? If you want to, you're allowed to assign values to those names. Right? So here's an enumeration for the 4 major compass directions. Right? North is 0 degrees, east is 90 degrees, south is 180, west is 270 degrees. Right? Here I've got the months. Right? I'm going to start numbering January at 1. I don't want 0. If you the first thing is always 0 unless you say otherwise. Right? So I want to start at 1, and then February will be 2, 3, 4, 5, 6, up to 12. Right? And now you can use enum day as a type, and you can use enum compass as a type name, and you can use enum month as a type name. Right? So I can say enum day d equals sun, right, for Sunday. Right? And I can say enum compass dir equals south, and I can say enum month m equals October. Right? When you print them out, unfortunately, you don't get these strings. You just get the numbers they correspond to. Right? So if you run that, right? D is 0, dir is 180, m is 10. Right? So you don't get the strings corresponding to them like you would in Java. Right? The Java enumerations, you would get the strings. Here you don't. The other problem is these aren't actually really types. Right? So even though you say enum day d equals sun, there's nothing preventing you from assigning some other value. So you can write enum day d equals 100 and everything would be fine. The compiler won't complain. Right? So these aren't really true types. They're just names for integers. But they exist and they are useful. Right? They're just not type safe. Okay, on its own, there's this word, so there's this type called void, which you've seen a little bit, right? So you've seen main void, right? Or you've seen some function returns the value void, right? Void means cannot hold any value, right? So you can use it as a function return type to indicate that the function does not return a value, right? You can use it as the only parameter to a function to indicate that the function has no parameters, right? And you should generally do that as a rule. So void. So those are the only 2 uses of void, except for pointers, right? So remember, so in the previous class, I told you what a pointer was, right? So if int star is a pointer to an integer object, or to an int object, sorry. Void star is a pointer that is allowed to point at anything, right? So it can point to any object. Right, so here's a little example. Here I've got an int x, right? Its value is 1, right? Now I can make a void pointer, right? So void star p, and I can point at any object that I want to. So for example, I can make that point to the object x, right? So void star p equals the address of x, and that's perfectly fine, right? What you can't do with a void pointer is you can't dereference it. Right? So you can't automatically dereference a pointer because the compiler doesn't know what type this is. Right? You've told it it's a void pointer, so it can point at anything. Right? So if you want to dereference that pointer, you have to tell the compiler what is that thing pointing at. Right? So here's p, right? That's a void pointer, right? So its type is void star. Right? If I actually want to print out the value of p, I have to tell it p is actually pointing to an int. So I have to cast to int, right? I have to tell it p is really a pointer to int, right? And then I have to wrap all of that up in brackets, and then I can dereference that, right? And so now I can get the actual value that p points at, which is just 1. Right? So there's a lot of things going on here, right? You got a pointer to void, you got a void pointer, it can point at anything. I've got a cast here to tell the compiler that, hey, that pointer p is really pointing at an int. And then I've got a dereference operator here to actually get the value of the int that's pointed at. Right? So when you run that, you get 1, because that's the value of x. Right? But I can use that pointer to point at anything. Right? So I can use p to also point at the double value y. Right? And that works just fine. Right? Again, if I want to print out the double value y, I have to tell the compiler, hey, p really points at a double now. Right? Then dereference that to get the value of the double, and then print that value. So that'll print out 2. So that's the program, so that's void, right? So you get 1 and 2. Right? So void pointers can point at anything. A little bit later in the course, we're going to use that to implement a generic data type. Right? I guess if you haven't, oh, this is going to be interesting. How many of you are taking 124 right now? Oh, that's not good. All right, so this is going to be interesting for you. It'll be a fun ride. So the generic stuff, I've assumed that people have taken 124 already, and they've seen generic types in Java. So I'll have to, it's a good thing I thought, okay, so I'll have to add a little bit of introductory material there. So you've all used like a list of double, right? Or a list of integer, sorry, or a list of string or something like that. Those are all generic types. You can do the same thing in C. It's just that when you go to store the values, you have to store them as pointers to void, because that's the only way that you can point at anything in C. Right? So you'll see the use of void pointers later on in the course. Okay, for now though, we're going to use arrays. So an array in C is similar to an array in Java. Right? Similar, not exactly the same. There are some differences. Right? So the similarities are an array in C and Java, it's just a contiguous sequence of objects all having the same type. Contiguous just means that they're all side by side in memory. Right? So there's one chunk of memory for the array, and then inside the array, you have the individual elements, right? With no space between the elements. Like Java, the number of elements in an array cannot change. Right? So you make an array, and that's it. You're stuck with that array for the lifetime of the array. If you need a bigger array, you have to allocate a bigger array, copy the elements into the new array, and then make your variable refer to the new array. Right? Just like Java, you have to specify the element type in C. Right? So arrays in C, you can have an array of int. You can have an array of double. Right? You can have an array of pointers. But the type has to be the same. And you use the square brackets to access the individual elements. Right? So again, the same as Java. One of the differences is when you make the array, you can actually put in the size when you declare the array. Right? So for example, you can write int x square bracket 3 to make an array of 3 ints. Right? So in this case, x is an array. It can hold 3 int values. Right? If you want to assign the values, you just use the square brackets. Right? So x0, x1, x2 gets 1, 2, and 3. Right? And then you can write a little loop and print out the values of the array. Right? So not surprisingly, this prints out 1, 2, 3. Right? Like that. Right? So that shouldn't be really surprising. The only difference compared to Java, you can put in the size of the array here. Right? Now, if you have an array that looks like this, right? So if you declare what's called a local or a, if you have a local array declared like this, you can ask for the size of that array. Okay? So size of ARR returns the amount of memory that's used by the array. Now it's the amount of memory that's used by the array, right? So it's not the number of elements, right? So it's the amount of memory, right? So the value that's returned by size of is the number of elements times the size of the element type. Right? Right? So here's, again, x is an array of 3 ints. Right? If I ask for the size of that array, right, I don't get 3. Right? I get 3 times the size of int. Right? If I want to know how many elements there are, then I have to divide by the size of int as well. Right? So this should be array 2. I just have to check. And it is. So I've initialized it a little bit different. I'll show you the initialization list in a minute. Oops, sorry, array 2. Right? Okay, so how much memory is used by the array? Well, 12 units of memory, right? So 12 times the size of car. Right? How many elements are in the array? Well, there's 3, right? Because size of int on my computer is 4. Right? It's 4. That's why you get the 3 there. All right, if you want to initialize your array, if you want to initialize your array when you declare it, you can use an initialization list just like you can in Java. Right? So here, int x square bracket makes an array. Right? If you give it an initialization list that has 3 elements in the list, that makes an array of size 3 for you. Right? So this makes the array x. Its values are x0 is 1, x1 is 2, and x2 is 3. Right? Now this is initialization, right? So you can only do this when you declare the array. Right? So I can write int x square bracket equals 1, 2, 3. What I can't do is the following. Right? So there's 5, that's fine. Right? So I can write that, this is fine, but what I cannot do is I cannot write this. Right? That does not work. Right? And this never works in C. So if you make an array, in this case x, right, you can never assign a value back to that array. Right? So assignment to an array variable is illegal in C. Right? So I cannot make x refer to another array in C. You can in Java, you can't in C. Right? So this doesn't work for 2 reasons. Reason number 1, that's an initialization list. It has to be used when you declare the array. Number 2, I'm trying to assign an array to an array. That does not work in C. Right? If you want to assign an array to an array in C, you have to copy all the elements from the second array into the first array. Right? So there is no array assignment in C. Okay, so that's fine. Notice that the number of initializers can be less than the size of the array. Right? So here I've got an initialization list with 3 elements in it. Right? I have an array, though, that can hold 5 elements. So the first 3 elements of the array get set to 1, 2, 3. The remaining elements get set to 0 in this particular case. Right? And that's guaranteed by the standard. Right? So the standard says that the rest of the elements shall be set to 0 for an array of int. So there's the example right there. This program does work. You can compile it and run it. Everything works just fine. Right. Strings are funny in C. So there is no proper, yeah, sorry, yes?
Can you add x6 and int?
Sorry, can I write what?
For int x5, after,
Yeah.
can you say x6 is this, and can it append or x6
Okay, so there's, you want me to, on the next line, you want me to write what?
x6 equals 5.
Like that?
Yeah.
Okay, can you write it? The answer is yes. Will it work? Who knows? That's the answer is who knows, right? So your legal array indexes here are 0, 1, 2, 3, and 4, right? Those are all guaranteed to work, right? Any number bigger than 4 will work, but it's not guaranteed to do what you want, right? So let's compile this. Array 3. I have no idea what this is going to do. Minus O, array 3 .c. So notice that the compiler does not complain. Yes? Right? No warning issued from the compiler. Oops, sorry, even though I've used an index that is not valid. Right? Okay, now what happens when I run this particular program? Okay, so in this particular program, right, now it complains. Right? So this one says something weird. It says stack smashing detected, terminated. Right? This isn't part of the standard, what got printed there. Right? This is a feature of the compiler. So the GCC compiler has some things built into it that helps the programmer, detect illegal or incorrect array element accesses. Right? The language does not check for you whether or not an index is valid, right? Unlike Python or Java, right? Python or Java, you try to access an element. If you try to use an illegal index, you get an exception, right? C doesn't do that. C just assumes, hey, whatever you wrote is what you wrote, right? Is what you meant to write, right? So if you ask for the 7th element of the array, it's going to try to give you the 7th element of the array, even though there's only 5. Right? That's the other thing. That's another one of the things you have to watch out for, right? C basically assumes the programmer knows what they're doing, right? Even though that's clearly not the case, right? So it doesn't try to save you from errors like this, right? The program will compile without any errors. It may even run without any errors. That's the crazy part. So this might actually run. You might actually be able to assign a value there, right? And everything might keep on going on its merry way, right? All right, strings. There's no actual string type in C, right? Unlike Java and Python, where you have a proper string type. Right? C simply says a string is just an array of char. Right? You can write a string literal using double quotes. Right? So that thing there, CISC220 inside double quotes, is a string as far as C is concerned. But really, it's just an array of char. Somewhere in memory, there's a chunk of contiguous memory whose contents are CISC220, followed by one of those. Right? So in C, a string is supposed to be terminated with the character 0. Right? Now, it's not the character that's equal to the digit 0. Right? That's different. It's equal to the character whose value is 0. To write that, you have to put \0 inside of a single quotes. Right? So \0 is the character whose value is 0. Right? It's also called the null character or the null terminator. Right? All your C strings are supposed to be null terminated. All string literals are guaranteed to be null terminated. Right? String literals are guaranteed to occur somewhere in memory, but it's read-only memory. You're not allowed to change the contents of that string. Right? Or you're not supposed to be able to change the contents of the actual string. Right? Is that true? Yeah, you're not supposed to be able to, if you try to access, you're not supposed to be able to change the elements of a string literal. This doesn't actually do that. Right? So that's a string literal, but we have an array whose contents is CISC220/0, right? And that array is str. Right? So if you print that out using %s, that will print out CISC220, right? So not surprising. Okay, so there's going to be, where do I talk about, is it here? No, I think we'll talk about strings in another lecture. Right? For now, strings are just arrays of char. And you're going to realize very quickly that this creates all sorts of issues that you have to deal with. All right. It turns out that arrays and pointers in C are very closely related. Okay? So arrays and pointers in C closely related. The name of an array is synonymous with a pointer to the first element of the array. Right? So I have an array called, I have an array called str here. Right? So the name str is exactly the same as a pointer to the first C. Right? So keep that in mind. Now what about subscripting? So when I write str square bracket 0 or str square bracket 1, that's exactly the same as pointer addition followed by dereferencing. So what do I mean by that? I mean the following. Okay, so here's my array str. Right? So it's just a string. In this case, it's a string CISC220. Right? I can make a pointer, right, to a char. Right? So P is a pointer to a char. So it points at some character somewhere. Right? And I can set that pointer to be equal to str. Right? So what does that do? Right? That pointer P, right? Remember, the name str is a synonymous to the pointer to the first element of the array. Right? So str is synonymous to the pointer to the first C in this array. Right? So in this case, the pointer P points at the C, the first C. Right? Now, I can go ahead and change what that thing is pointing at, right? So I actually have access to the first character C in this array str. I don't have access to the character in the string literal, right? I have access to the character in the array str. So if I write star p, right? Remember what star p does? That dereferences the pointer. So that gives me the object C, right? And I can change that to lowercase c, right? And that works. So now you have the string lowercase c, big CISC220. Right? So I can change an element of the array using a pointer. This turns out to be enormously useful later on. Right? Now, how do I get to the I? Right? So how do I get to the I? If I want to change that I, well, I could write str1 equals something. Right? I could write str1 equals something. Right? Or I can take that pointer p, and I can add 1 to it. Right? So when you add an integer value to a pointer, right? So if I add the value 1 to p, that goes to the next element in the array. Right? So if p is pointing at the c, right, then the pointer p plus 1 points at the I. Right? The pointer p plus 2, right, p points at the c, p plus 2 points at the s. Right? P plus 3 points at the second c. Right? And so on and so on. If I dereference those pointers, I can actually change the value of the objects that are pointed at. Right? So p plus 1 points at the I. Star p plus 1 gives me the object big I. Right? Or it actually gives me the element str1. Right? And I can reassign that value to lowercase I. Right? So that's the same as writing p1 equals I, which in this case is the same as writing str1 equals I. Right? P plus 2, well, p points at the c, p plus 2 then points at the s. Right? Dereference that to get the character that's actually pointed at and set that to the c, s, lowercase s. Right? And so on and so on and so forth. Right? So you can effectively treat an array as though it was just a pointer. Right? And this will also have a big impact later on in the course. All right, anybody have any questions about that? It's definitely weird the first time you see it, and the second time, and the third time, and the fourth time. Right? You have to do this a bunch of times before you get used to it. It's very strange. Yes?
On the use of p open bracket 1 close bracket syntax, do you need p asterisk in front of it or no?
Do I need p asterisk? The answer is no. Where's my, here it is, okay. So, P4, what should we change this course to? How about we change it to 320? There we go. Right, so this is array 5, okay. It's 320. So that works just fine. Right? Now you remember, why does that work? Why does that work? It's because p, it's a pointer to the first element of the array. Right? That means it's synonymous to the array. Right? So I can also, right, so that's exactly the same as writing str whatever. So str5 equals, you can also change that to a 3. Right? And that also works. Right, so if you go back and compile that and rerun that, right, you now have CISC220. Yeah, question at the back?
If you wanted to access the whole thing, is that possible?
You mean the whole thing at once?
Yeah.
No.
Say, no?
No. So what was your example going to be?
Well, you say like in Python you have a list that said like CISC220 was at index 1, and index 2 would be like CISC221.
Right.
Is that plausible?
Oh yeah, it is possible. So you want an array of strings.
Yeah.
Yes, that's possible. I don't know if you want to see what it looks like. I don't think any of you want to see what it looks like. So you want an array of strings, right? So I need an array of string, right? So I need an array. So what am I going to call this? Let's call it strings, right? So I need an array of strings, right? So what type has to go into here, right? Well, I need an array of something, right? So that is what an array of strings looks like. Car strings, whoop, right? So you end up with an array where all the elements are pointers to car. Yeah. And I will just put in some commentary. Right. Right. And so this is a consequence of the fact that C doesn't have a proper string type. Right. Now, there's nothing from stopping you from making a string type. Right. So you can define a type called string where you hide all of this stuff from the user, which is exactly what the string class is in Python and Java. Right. Python, the classes, they're just a way of hiding all this stuff. C doesn't hide anything from you. Okay, there's no array index bounds checking in C, right, which I've explained already. So when you're writing programs that involve arrays, you're really going to miss the exceptions that you get in Java, right? Because Java and Python, they both check the indexing for you, right? If you use an invalid index, then if you're lucky, your program crashes, right? So we saw an example of that earlier. We saw an example of a program that did crash. If you're unlucky, your program does not crash. Something gets overwritten, and your program keeps on going along its merry way, right? So there's no guarantee that the program crashes. And it could run. It may run forever, and you may not know that there ever was a problem. And that's just the way it is, right? So here's an example. So there's my string. I have an array of car, right? It's the string CISC220. There's my pointer to the string, right? So there's my pointer to the first C. I'm going to change the first C to the lowercase c. Now I'm going to use the pointer p, and I'm going to try to access the 100,001 element of the array. And I'm going to set that to the question mark, right? Does this work? I have no idea this works. Let's see what happens. Now, the problem is I've got so many tabs open that it's going to be hard to find. Array 6. Is this the one? It is. Okay. Alt tab. Well, let's see what happens. Okay, so in this case it barfs, which is good, right? However, let's compile it. Array 6.c. Okay, notice that it compiles without any warning, right? So even if you turn all warnings on, which you can do with minus big WALL, right? So that turns on all compiler warnings, right? You get no error, right? There's no bounds checking in C. There's a way to, let's see, hang on. Here we go. There is an example here. So you can, in fact, make this program run, right? So I guess we'll do this. It's already 20 after, so I should stop. So here's an example where I'm going to access an element that's beyond the end of the array. And it turns out you can, in fact, do this and have your program keep on running. Right? So we'll show you that. Or you can try this at home in the next class. Right? All right, see you, I guess, tomorrow, right?